In this video, we're going to look at how the approximate position of roots of the equation f of x equals 0 can be found through the process of searching for a sign change in the function f of x. If we say that the number x lies in the interval square brackets 3, 7, close square brackets, then that is the same as saying that the number x satisfies the inequality 3 is less than or equal to x is less than or equal to 7. If on the other hand we say that the number x lies in the interval open square brackets 3, 7, close with rounded brackets, then that is the same as saying that the number x satisfies the inequality 3 is less than or equal to x is less than 7. If we say that the number x lies in the interval open rounded brackets 3, 7, close with square brackets, then that is the same as saying that the number x satisfies the inequality 3 is less than x is less than or equal to 7. And finally, if we say that the number x lies in the interval open rounded brackets 3, 7, close the rounded brackets, then that is the same as saying the number x satisfies the inequality 3 is less than x is less than 7. The second idea we must introduce here is the idea of a continuous function. And a function is continuous if its graph can be drawn with a pencil fully without taking the pencil off the paper. So, for example, the function f of x equals x minus 10e to the minus x, defined on the interval 0 is less than or equal to x is less than or equal to 5, is shown in the diagram. It's clearly continuous because we can draw this graph without taking the pencil off the paper. On the other hand, if we consider the function g of x equals tan x, defined on the interval of numbers 0 is less than or equal to x is less than or equal to pi, then we obtain the graph seen in the diagram. We can see that the graph jumps at x equals half pi from large positive values just before x equals a half pi to large negative values just after x equals a half pi. I could not possibly draw this graph with a single curve without taking my pencil off the paper. So this graph is not continuous on the interval 0 to pi. Now the main purpose of this video is to show a method for locating the roots of the equation f of x equals 0 through sign changes. So let's suppose that we've got a function f of x which we know is continuous over the interval a is less than or equal to x is less than or equal to b, and that the signs of f of a and f of b are different. So f of a might be positive and f of b might be negative. On the other hand, f of a might be negative and f of b might be positive. So let's have a think how that might happen. So in this case here we've got f of a is positive, we've got f of b is negative, and the graph might do something like that. But we've clearly got a position between a and b where f of x equals 0. However, a graph with f of a positive and f of b negative may be a little bit more complicated. And in this case, there are 3 positions in between a and b for which f of x is equal to 0. In this case, we've got f of a is negative and f of b is positive. The graph might look something like that, in which case there is one solution of f of x equals 0 in between x equals a and x equals b. Or the graph might be a bit more complicated and look like this, in which case we've got two roots of the equation f of x equals 0 in between x equals a and x equals b. Now these sketch diagrams should make it clear that if f of x is continuous on the interval a is less than or equal to x is less than or equal to b, and the signs of f of a and f of b are different, then the equation f of x equals 0 has at least one root in the interval a is less than or equal to x is less than or equal to b. We call this the sign change in a continuous function result. So for example 1, if we want to prove that the equation 0.3x squared minus sine 2x minus 3 equals 0 has at least one root in the interval 2 is less than or equal to x is less than or equal to 4, then we'll let f of x equal 0.3x squared minus sine 2x minus 3. Now we know the curve of x squared is a continuous curve, we know the curve of sine 2x is a continuous curve, and we know the curve y equals 3 is a nice continuous line in fact. So f of x is going to be a continuous curve. There's no problem about the continuity of f. If we consider f of 2, we've got f of 2 is minus 1.04, we've got f of 4 is 0.81. So making use of the result that we've just introduced, we notice that we have got a sign change in a continuous function, so there must be a root of f of x equals 0 in the interval 2 is less than or equal to x is less than or equal to 4. So the equation 0.3x squared minus sine 2x minus 3 equals 0 must have a root in the interval 2 to 4. There may in fact be more than one root. Moving on to a second example, we've got to explain why the equation 3x to the power 5 plus 7x cubed plus 2x minus 160 equals 0 has just one real root, and we've got to find consecutive integers between which the root must lie. So if we let f of x equal 3x to the power 5 plus 7x cubed plus 2x minus 160, f of x is a polynomial. We've drawn lots of polynomial graphs in the past, and we know that they have got no discontinuities. In other words, f of x is a continuous function. If we consider the derivative of f of x, well, the derivative of f of x is 15x to the power 4 plus 21x squared plus 2. Now we know that x to the power 4 is always non-negative. We know that x squared is always non-negative. And we know that 2 is definitely a positive number. So therefore f dash x, the gradient function, is always positive. Which means that the function f of x is not only continuous, but also strictly increasing. So the curve y equals f of x crosses the x-axis at most once. So the equation f of x equals 0 has at most one real root. Now if we do a short integer search, we could say f of 0 is minus 160, f of 1 is minus 148, f of 2 is minus 4, but f of 3 is 764. So that tells me that I know that I have got at least one root in the interval 2 is less than or equal to x is less than or equal to 3. And that is my sign change in a continuous function result again. So putting the two things together, I know that f of x equals 0 has at most one real root. I also know that f of x has at least one root between x equals 2 and x equals 3. So by putting those two results together, I can say that f of x equals 0 has exactly one root, and that this one root lies between x equals 2 and x equals 3. Moving on to our third example, we've got to determine graphically the number of roots of the equation e to the half x minus 5 equals 0, and determine the integers between which the root or roots lie. Drawing the graph of f of x is not particularly easy. However, if we do a little bit of rearranging of the equation, we can say that e to the half x minus 5 equals 0 is the same thing as e to the half x equals x plus 5. In other words, the roots of the equation are given by the x values of the points of intersection of the curves y equals e to the half x and y equals x plus 5. So my graph of y equals e to the half x is an exponential growth graph. The graph of y equals x plus 5 is a straight line passing through minus 5, 0 and 0, 5. We can see from the sketch diagram that there are certainly 2 roots to the equation. If you think about the graphs of the 2 functions, then you ought to be able to produce a reasonable argument about why there are no other points of intersection between the 2 graphs. The negative root looks to be very close to minus 5. So if we evaluate f of minus 5, we get 0.082. If we calculate f of minus 4, we get minus 0.864. That, remember, is f of x is e to the half x minus 5. So, sign change in the continuous function tells me there is at least one root in the interval minus 5 to minus 4. Looking for the positive root, well, f of 4 is minus 1.61. F of 5 is 2.18. So again, sign change in our continuous function tells me that I've got a root in the interval 4 is less than or equal to x is less than or equal to 5. Our final example considers the diagram of the graph y equals 1 over sine x minus 3. Charlie observes that for the function g of x equals 1 over sine x minus 3, g of 0.2 is 2.033, and g of 0.4 is minus 0.432. Now the interval 0.2 to 0.4 is certainly inside the interval of 0 to pi, and the graph is continuous on the interval 0 is less than x is less than pi. There will be jumps at 0 and pi, but that doesn't matter, it's continuous provided x is greater than 0 and less than pi. So Charlie has a sign change in the interval 0.2 to 0.4, where g is certainly continuous. So there must be a root of g of x equals 0 in the interval 0.2 to 0.4. So Charlie can say that the equation g of x equals 0 has a root in the interval 0.2 to 0.4. Harrison observes, though, that g of 3.1 equals 19.0 and g of 3.2 is minus 22.13. And he concludes that the equation g of x equals 0 has at least one root in the interval 3.1 to 3.2. Unfortunately, Harrison has ignored the fact that the graph of g of x has a discontinuity at x equals pi, and x equals pi is in the interval 3.1 is less than or equal to x is less than or equal to 3.2. So Harrison's use of sign change in a continuous function is not applicable because we have not got a continuous function between 3.1 and 3.2. And that concludes our look at finding roots of the equation f of x equals 0 through a sign change.